Hey there, welcome to my channel on chemistry lessons. You know the drill by now. You don't want to miss new releases, new lessons. So at the moment, all the lessons that come out are designed to be full lessons following either the BTEC or AQA specification. In future, I hope to be releasing some like short, snappy revision type videos just to cover key concepts. So this lesson is going to cover AQA A level, and the specification, it's going to be a physical chemistry, and it's a first year topic. It's an AS 3.1.4 energetics, and it's going to be on Hess's Law. So it's lesson 2 of a series of 3 lessons on the 3.1.4 energetics scheme. And although this spec point appears fairly small, so it is a fairly small spec point, there's quite a lot of application, as a lot of physical chemistry is. So we need to know what Hess's law is. So we need to understand and define Hess's law and be able to perform calculations. Okay, so there's some very standard ones that we're going to look at to start with. So a definition of Hess's law then is that the enthalpy change of a reaction is independent of the route taken, provided that the start and end conditions are the same. So the key point is that the enthalpy change is independent of the route taken. Let's try and have a look at what that even means. So how do we explain that? So here we've got an enthalpy change. This here is an exothermic enthalpy change. We've got a decrease in enthalpy. And this here is a negative. It's an exothermic. Now, this could be route 1. So this could be one way of getting from reactants to products. So that's route 1. We could have a second option or a second route possible, where we could have a reaction, we could measure the enthalpy change of the reactants down to some sort of intermediate. I'm going to have an intermediate down the bottom here. So we have an intermediate, and this enthalpy change could be, let me just say A, and this is exothermic as well. And we also have a possible enthalpy change from here, and this would also be exothermic. Now, what we find in here is that enthalpy change 1, so there's one way, this is route 1, and route 2 could possibly be, so route 1 was direct from reactants to products, route 2 could be down to the intermediates and then back up to here. So the start point, there's my start, and there's my finish. The start and finish points are still the same, so route 1 has got there directly, route 2 has gone indirectly through an intermediate. So route 1 is equal to delta H. That was route 1 there, it was just equal to delta H. And route 2 was in fact minus B, so it was this one. But then I was going up against, I was going in the opposite direction to A. So it's plus A. So that would be showing how I could calculate an enthalpy change from 2 different routes. And I'm just using Hess's law that route 1 was equal to route 2. It's easier if we kind of look at a couple of examples really, and we try and apply what this looks like in an exam question. So here we've got a very general reaction here. We've got an enthalpy of reaction. We've got A plus 2B going to C plus D. And we've been asked to calculate the enthalpy of reaction from the combustion data. So you're always given, in an enthalpy or a Hess's law question, you're always going to be given some information, okay? Now, we've got the reactants, products, and we've got an enthalpy change. Now, we've been asked to calculate this enthalpy change using some different data. Now, we've been given, the key thing is, what data have you been given? We've been given combustion data, look. We've been given the combustion data. So what we can do is we can take A and we can combust A. And that would be minus 10, because I'm taking the value here. The enthalpy change for 1 mole of A is minus 10. I'm then going to take B and combust B. Now, 1 mole of B is minus 5, but we've got 2 moles of B. So it's going to be 2 times minus 5, which is going to be minus 10. Okay, so what I've actually just calculated is to go an A plus 2B down to an intermediate. I can combine those together, and that value will be minus 20. It's minus 10 for A and minus 10 for B, or for 2B. So this arrow, this green arrow, is a combination of the two, and it's minus 20. Okay, so let's turn our attention to the other side then. We've also got the combustion value for C, minus 20, and that's 1 mole. Likewise, I've got the combustion value for D, that's also 1 mole, which is minus 2. So I can do the same here. I can come up with one total value for my products down to the intermediate of minus 22. Okay, so what I'm going to do now is I'm going to calculate my enthalpy of reaction. So root 1 is this way, look, there's root 1, which is equal to enthalpy of the reaction. Root 2, I'm going to have my start and my finish in the same place. So this time, start and finish, I could go this route. And this time, root 2 is equal to, I'm going down with this arrow, look, I'm going in the direction of the green arrow, so that's minus 20. But look here, I'm going up against these arrows, I'm in the opposite direction. So instead of being minus 22, it's plus 22, okay? And using Hess's law, root 1 is equal to root 2, because they have the same start and the same finish. So using Hess's law, root 1 is equal to root 2, so enthalpy of reaction is equal to minus 20 plus 22, which equals plus 2, and I'll put my units back in now, kilojoules per mole. Okay, so what I've done is I've applied Hess's law, I've used the data I've been given, and I've calculated the enthalpy of reaction. Okay, now hopefully you can see the logic, you can see the flow there of how I've managed to come up with those values and where they've come from. However, what you can remember, there is a formula you can just remember. If you want to calculate the enthalpy of reaction and you've been given the combustion values, okay, it's the sum of the enthalpy of combustion values of the reactants, take away the sum of the enthalpy of combustion of the products. You can just use that formula. However, it's far more advisable to understand the process of using Hess's law, because this will help us in the really difficult exam questions. So just to point that out then, we've actually done the reactants take away the product and the sum of the reactants. So the sum of the reactants is 1A plus 2B, which is minus 20. Take away the sum of the products, which is minus 20 minus 2, and it's only 1 mole. So minus 22. So you see, you can get yourself in a little bit of a muddle sometimes if you're not careful with the signs. So minus 20 minus minus 22 is plus 2. So we showed very little understanding to get the same answer just by using the formula. I'd far prefer and advise that you can understand, and this is known as a Hess cycle. I've drawn a Hess cycle, okay? Let's take this to some exam questions then. So I advise that you have a go yourself. So you pause the video first and have a read and have a go. We've got a few different exam questions we're going to do. Hopefully you will see a very clear pattern emerging. So pause the video, and when you're ready, unpause. Okay, so I'm not going to write the definition for the enthalpy of combustion, although I will give it. It's from the lesson 1, this one. The standard enthalpy of combustion is the enthalpy change when 1 mole of a substance completely reacts with oxygen under standard conditions. It's a very nice 3 marks, these definitions, and I did point out in lesson 1 that you do need to know, there's certain definitions you do need to know, and they were all shown in lesson 1. Right, let's get on to our Hess question though. 3 marks here. So we've been given an equation, and we're told that it corresponds to the enthalpy of formation of propan 1-ol. and we've been given some data, and it asks us to use the data to calculate a value for that enthalpy of reaction. Well, what I'm going to do is I'm just going to draw the equation out. Just to speed things up, I'm not going to put the state symbols in. So there we go. So I've just copied the equation out just so you can see my Hess cycle. And what have I been given? I've been given the combustion values. So I can draw an arrow down here, an arrow down here, arrow down here. Combustion of 1 mole of carbon is minus 394. So it's going to be 3 times minus 394. The combustion of 1 mole of hydrogen is minus 286. So it's going to be 4 times minus 286. Combustion of oxygen is not in the table. And that's because oxygen reacting with oxygen, we're not going to get a reaction. So we don't need to worry about this arrow here. It's going to be a 0 change. Oxygen reacting with oxygen, it's not going to happen. So we're going to have a 0 change. We can ignore that arrow there. And we've been given the enthalpy of combustion of CH3, CH2, CH2, OH, and it's 1 mole. So it's 0, 2, minus 2, 0, 1, 0. Right, okay. So we want to calculate enthalpy of reaction. We want to calculate this, which is root 1. And our root 2 is going to be here, here. And we're going to use Hess's law that root 1 is equal to root 2. You may even wish to write in the question, in your answer, sorry, using Hess's law, root 1 equals root 2. We don't know what root 1 is. That's the whole point in the question. And root 2 is minus 3 times 394. So it's 3 times minus 394 plus 4 times minus 286. And then it's going to be minus 2010. Because I'm going against this arrow. Look at the direction of this arrow compared to the direction of this arrow. So this arrow coming down is minus 2010. Therefore, when I go against that arrow, doesn't change numerically in terms of magnitude, but the sign will. It will become positive. Okay, so it's a minus minus. That becomes plus. And you'll work your way through that. I'll let you work that out on your calculator. But the value that you should get to here is minus 316 kilojoules per mole. Okay, next question then. Again, pause, have a go yourself, and when you're ready, press play. Definition for enthalpy of formation then. Enthalpy of formation is the enthalpy change when 1 mole of a substance is formed from its elements in their standard states under standard conditions. B. Use the table to calculate the enthalpy of formation of liquid methyl benzene. So there's some unfamiliar things here. You're probably not familiar with these substances such as methyl benzene, but that's not an issue because we don't need to worry about that. We're going to construct a Hess cycle. This is 7 times minus 394 and 4 times minus 286. And then on this side, minus 3909. And then we can apply Hess's law. We've got root 1. And we've got root 2. Root 1 is equal to root 2, which is equal to 7 times minus 394 plus 4 times minus 286. So that's a sum of the reactants. Take away minus 3909. And we have a final answer here of plus 7 kilojoules per mole. Okay, third question then. 2 more to do with enthalpy of combustion before we move on. So pause the video, have a go, and when you're ready, let's go through it. Right then, so starting to feel very familiar now. we've got 3 combustions coming down here. It's 2, so this side is 2 times minus 394, 3 times minus 286, and 1 times minus 297. And for the products coming down here, it's just 1 times minus 1170. So applying Hess's law, root 1 is equal to root 2. We're going to end up with a value of minus 773 kilojoules per mole. Next question then. So we've been given some enthalpy changes, slightly more complex this one. So we've got a couple of reactions there, and we've been asked to use the standard enthalpy of combustion data below to give a value for the standard enthalpy change of the following reaction. Okay, here we go. So 4 carbon solid plus 2H2 gas plus 2O2 gas goes to C4H4O4. So let's have a look at constructing a Hess cycle then. Minus 1356 here. And for our reactants, we've got 4, 2, and again, we're not going to see a value for this because we're not going to have the combustion of oxygen reacting with oxygen. That's going to be a 0 enthalpy change. It's not going to take place. So carbon is 4 times minus 393.5 and 2 times minus 285.8. And applying Hess's law now, root 1, which is the enthalpy of reaction, is equal to root 2, which is down, and back up again. And so it's 4 times minus 393.5 plus 2 times minus 285.8 minus 1356. And we come up with a value here of minus 789.6. My advice, if you're struggling getting the answers on these few questions, it's quite possibly calculator error. So what you can do is, a bit of advice would be to work out a value for this and then just have one number here. And then you've got one number for your green arrow as well. Okay, so you have one number here, which we do anyway, and you have one number for the reactants. So you can work out the sum of the reactants. Okay, so you are, at this point when you're doing your Hess cycle, you are in fact applying the formula, the sum of the enthalpy of combustion of the reactants take away the sum of the enthalpy of combustion of the product. So you are actually applying that formula when you apply Hess's law. Okay. Okay, this time then we're going to calculate the enthalpy of reaction. This time, instead of using combustion data, we're using enthalpy of formation data. Okay. And this won't always be that clear in the exam. So this is the mistake people will make when they're constructing their Hess cycles, is they'll get their arrows mixed up in the wrong direction. And quite often it's because they don't truly understand the values they're being given. So in the last set of questions, we had been given combustion values. This time we've been given formation values. It's up to you to make sure that you look for that in the question. So this time, if we've been given formation values, we apply the same logic of Hess's law. So we're going to have a root 1 is going to be our enthalpy of reaction. This time, root 2 will still be the same. Root 2 is going to come down here and up here. So root 2 will still make that same V from the reactants down to an intermediate and back up to the products. So that's the same. The only thing that's going to change here is the direction of the arrows, because this time we are forming 1 mole of C. So the arrow will point towards the C instead of away from it. And likewise, pointing up because we are forming them. So that's the big difference here, is the direction that the arrows are pointing. Notice when I've been given the formation values, the values are pointing towards that substance. just by definition. And this, again, formation of A is minus 10. The formation of 2B, so this is going to be minus 10 as well, because I've got to take into account molar ratios. So I'm applying Hess's law exactly as I did last time. So root 1 being equal to root 2. And root 2 is, this time I'm going against these arrows, look. So this time it's plus 20 because I'm going against those two 10s. I'm going down. So from here to here is plus 20. And this time I'm going with these arrows, so I don't need to change the sign, minus 22. So this time the enthalpy change is minus 2 kilojoules per mole. Time for us to look at some exam questions then, okay? So pause the video, and when you're ready, unpause and we'll have a go. Right, so it's quite obvious today because I've split it into two very clear sections. One where we've been using combustion data, one where we've been using formation data. And as you do a few, you get used to the pattern. But what you got to remember is in the exam, you won't necessarily know which one it is, and you've got to look, okay? So as you'll see in the question, it doesn't mention anywhere about the values you've been given. It just says you've been given them, and we've been given formation values, okay? So we've also been asked to state Hess's law and use it. So I'm not going to write it down, but Hess's law is the enthalpy change is independent of the route taken, provided that the start conditions and the final conditions are the same. Right, so now I'm going to construct my Hess cycle. So I'm going to draw the equation out. This time, when I find my values, the arrow is going to point towards them because it's formation. So this is minus 642, and this value is minus 286. And again, I probably suggest or advise that you come up with one value. You combine those two before you do the final big calculation on your calculator. So you're going to end up with a value here. And for the reactants, we've got 1 mole of this and 2 moles of this. So this is minus 602, and this is 2 times minus 92. And again, you can come up with a value from here to here. Okay? So this time, when we apply Hess's law, we've got root 1, root 2, so it's still the same idea. You just got to be careful on the values that you're about to put in. So root 1 is enthalpy of reaction, root 2 is equal to root 1 because we're applying Hess's law, and the final value is going to be, got to change these signs so it becomes plus 602 because I'm going against these arrows this time, going in the opposite direction, plus 2 times 92, minus 642, minus 286. My answer here is going to be minus 142 kilojoules per mole. Again, if you don't get the correct answer, but you seem to understand the theory, come up with two values, okay? Because actually what we're doing here, we could remember a formula here. If you've been given formation values, then this time it's the sum of the enthalpy of formation of the products, take away the sum of the enthalpy of formation of the reactants. It's the other way around. So if you've been given formation values, it's the sum of the products, take away the sum of the reactants. Whereas when you've been given the combustion value, it's the sum of the reactants, take away the sum of the products. And that is simply because of the direction of these arrows. Next then, okay? Pause the video, have a go, and when you're ready, unpause. Okay, so let's have a look. We've got a formation values. There we go, formation value. And this is minus 248. We don't have a formation value there. Let's see, we'll come back to that in a minute. We've got a formation here. This is going to be 3 times minus 286. and this here is 3 times minus 394. Now the reason we've not been given a formation value for this, because think about what the definition for formation means. It's the enthalpy change when 1 mole of a substance is formed from its elements in their standard states, standard conditions. Now, to form an element, which oxygen is an element, to form an element from an element requires no change. So this is in fact 0. So if you've got an element in its standard state, I don't have to do anything to it in terms of formation. So I can just ignore this when it comes from a formation calculation. So this time, root 1 and root 2 is going to be equal to, so plus 248. Notice how I've changed the sign. I've gone against this arrow here. Then it's plus 3 times minus 286 plus 3 times minus 394 equals to minus 1792 kilojoules per mole. Again, advice is if you make a mistake with the calculator, have one value here to avoid having to do this on your calculator at the same time. Okay, some people do make silly calculator errors there. Okay, last one then. So pause the video, and when you're ready, unpause, you know the drill. Right then, so why are the values standard enthalpy of formation of carbon and nitrogen 0? Well, because they are elements in their standard states. They are elements in their standard states which require no change. State Hess's law. Hess's law is the enthalpy change is independent of the route taken, provided that the start conditions and the final conditions remain the same. Okay, so let's apply our cycle now for the last one. We've been given formation values. So the arrow is going to point up. There we go. I don't need a value for that because it's an element. This one and this one. Likewise, I don't need a value for that because it's an element. As you can see, they are 0. And formation here is minus 365. Formation of CO2, we need to do a half times minus 394. And water is 2 times minus 242. Apply Hess's law of root 1 is equal to root 2. And we get a value of minus 316 kilojoules per mole. Hopefully that was useful. Any suggestions or any other things you want, let me know. There it is. Good luck.